So far we have the school from Sofia, the Vocational High School of Electronics, John Atanasov. We have the National College Grigor Muazil in Bucharest, in Romania. We have Ελληνογερμανική Αγωγή High School in Athens, Greece. And we have the Leo Bike Senior High School in Haifa in Israel.
Excellent. Hello, everybody. So we're gonna go to the South Pole soon. Maybe should I introduce Atlas and you can introduce CMS?
Absolutely,
or do we
yeah.
go straight to the South Pole. Okay, let me just. I'll tell you where I'm at, and then you guys can tell us where you're at. Hello. So my name is Steve Goldfarb, and I'm a physicist on the ATLAS experiment, and we're exactly across the ring from my friends over at the CMS experiment, which is where Angelos is at the moment. ATLAS and CMS, you guys know, we're the two guys who discovered what? Who knows?
The Higgs.
Yes, the Higgs boson. We discovered the Higgs boson. Don't tell anybody, we actually lost it, but we're going to find it again, and we'll have it before next year, okay? But don't tell, it's quiet, you know. You know, it took us a long time, it took us 50 years to find it, and so it's probably behind my couch or something. We'll find it again. This is the ATLAS experiment. I'm just kidding. You don't lose a particle once you find it. This is the ATLAS experiment. Behind me is the control room. This is where my colleagues and I, where we spend time when the LHC is operating, when there's collisions. We're at one point where there are collisions on the LHC. CMS is at another point all the way across from us. But we also have friends who aren't going to be with us today, but down in one direction called LHCb, people who are trying to answer the question of why there's matter and we don't seem to see antimatter left over in the universe, naturally. And we also have friends the other way around from an experiment called ALICE, who are really trying to study the very early universe before protons were born. That's even before Angelos was born, way back when. This is, 10 to the minus 6 or seconds or something like this after the Big Bang, a long time ago before protons were born. ATLAS and CMS, we're just trying to explore. We are enormous, powerful microscopes trying to look into matter to see what there is there. And we're going to talk more about that when we get back. I think that's all I really have to say from ATLAS. Maybe you want to tell us what's going on over at CMS, Angelos?
Yeah, thanks, Steve. We are just on the opposite side of the LHC ring. We are located in France. As you know, the LHC ring crosses the Swiss and France border. Most of the ring actually is located in France. We are situated in a place called Cessy, okay, and I'm located in the CMS control room. It's not as fancy as the ATLAS control room, I have to say. It's slightly smaller. Maybe I can turn a bit the camera here a little bit. Maybe you get a glimpse of lots of computers and a few people now in the morning shift, working. Most of the work right now is happening actually 100 meters underground, guys, where lots of engineers and physicists are testing the detector in collaboration with the engineers of the LHC, and they are almost ready to start colliding particles. Okay, this will take a few months. This is part of the long shutdown project, which is gonna finish next spring. Okay, so we're all in sync. We are all actually collaborating here together to make this new run, which is gonna last for 3 years. At higher energy levels, actually at the highest so far energy levels, okay, that the LHC has been designed. So far we've been colliding protons, okay, at energy levels of 3.5 tera electron volts and 3.5 tera electron volts, okay, so 2 beams of protons colliding. Now we are upgrading the LHC, and we will eventually reach a total collision energy level at 14 tera electron volts. So lots of amazing things actually are around the corner. So that's all for now. I think it's time to switch to South Pole, right?
So, Angelos, just to check with you, we're all going to now click on WebEx, and we're all going to be listening on WebEx to the South Pole. Okay.
Yeah, exactly. So we're going to leave now video, okay, guys? You are going to go to switch to WebEx. So Jim and Megan will be there to assist you. It's going to be an audio connection, so you're going to hear the scientists down to the South Pole, okay, talking to you. You're going to have a very nice visuals and photographs to give you, a very nice overview of what's going on in the groundbreaking experiment of 2013, IceCube. So we'll be back around 9:50. Okay, so Jim and Megan, when they finish the session, they're gonna ask you to switch to video. So we will all be here in 45 minutes.
Okay, we'll see you soon.
Okay, thank you.
Get your coats on.
You guys.
Get your coats on. Get warm. We're going to the South Pole.
Okay, so everyone should be seeing the slide that says Extreme South Pole Science. And if there's any issues throughout the connection, please just send me a message. You can send the message to Kim Krieger, host. Once again, that's Megan in Madison, Wisconsin. Sorry for the confusion. And I'll turn it over to Jim, and he can introduce our guests from the South Pole.
Hello, everyone. We're very excited to connect across the world tonight, or what's tonight for us. It's, I guess, in the morning for you all. So I'm Jim Madsen. I'm at the University of Wisconsin River Falls, and we're very excited to have our winter overs for the IceCube project, Ian Reese and Dag Larson. So we'll go to the next slide. So I'll let Ian and Dag say hello.
Hi everybody, I'm Ian. I'm the guy on the bike on the left-hand side.
And hello, I'm the guy on in the white coat on the right picture.
Very good. And can you just say quickly, Ian's outside there, but Dag, where is that location you're at?
This is inside the IceCube lab where we have all the servers and all and everything else which is processing the information which we collect from IceCube.
All right, very good. That's good. Okay, next slide. Okay, and I already introduced myself. That's me when I deployed to the South Pole, getting on the plane in Christchurch, New Zealand. And Megan, do you want to say hello?
Hi, once again. I'm Megan, joining you from Madison, Wisconsin, and I work with the Education and Outreach Group on IceCube. So we're very excited to have everyone joining today.
Okay, next slide. Okay. A few words about this picture.
Ian here. Yes, that's basically the winter over crew here at South Pole Station. South Pole gets too cold for most of the year to fly airplanes down here, so we have a pretty distinct summer and winter season. We're just wrapping up the winter right now. There's 41 of us. I think a good fraction showed up for that photo. But basically, we've been here since for last year, and we're just wrapping up basically a full year at South Pole where there have not been any planes since the 14th of February.
Yep. Great. So I'm sure there'll be some questions about that later. Let's go to the next slide. Okay. And is this sunset or sunrise?
Not sure. Sorry. It's one of the two.
It's very similar.
Guess, it's probably sunset.
Yeah.
Yeah.
It's a much different situation where you basically have one long sunset, right, a year, and then one long sunrise, right?
That's right. And one thing that makes it a little bit weird down here is that the sun sort of spirals through the sky, so you can actually tell the time of day from where the sun is, but where it is on the horizon. But like I can't look at that picture and tell you whether it's a sunset or sunrise just based on the direction of it because we don't know what time of day the picture was taken.
Yep. Yeah. So we have a video a little later showing 24 hours of the sun, just as Ian described. Okay, next slide. Okay, the IceCube Neutrino Observatory really has not much of a footprint above the ice. Really, the only thing that sticks up is the building in the lower right there. That's the IceCube Laboratory. The little dots that are in the picture in the upper half there aren't actually on the snow at the South Pole, but they're just there to show you where we drilled holes in the ice. It's difficult to get a perspective of how big this is, but each one of those dots is about 125 meters apart. And then that graphic in the lower left we'll talk more about in a moment. That's how we show the types of events that we're recording with our sensors down in the ice. So let's go to the next slide. The IceCube collaboration now is approaching about 300 members. This just gives you an idea of where our partners are located. There's 17, I guess now we have a couple more joined, so maybe up to 19 in the U.S., a couple in Canada, and then we have about 26 institutions outside the U.S., so the majority in Europe, but then we also have South Korea, Japan, Australia, and New Zealand. Next. So I'm going to give you a 1 or 2 minute description of how we built the detector, because it was an amazing technological achievement. So the ice at the South Pole is almost 3,000 meters thick. And what we did was melt holes 2,450 meters down, 60 centimeters in diameter, and then we lowered a cable down that had those light sensors that are shown on the left side here. They're called a digital optical module, and basically they're just very sensitive light detectors. So they take in some light and then actually produce a pulse of electricity, and then that pulse of electricity is recorded, and each one of those little sensors acts as its own computer and basically sends the equivalent of like a text message to the surface saying, hey, I saw something, here's how much I saw, and then to about a billionth of a second, the time at which it saw it. Then the electronics on the surface that Dag showed you that was standing next to take in all those messages and see whether there was an actual particle that went through the ice that produced those flashes of light. About 300 times a second or so, those light sensors say they saw something, but it was really just what we call electrical noise. There isn't a real signal. So we have a number of different ways that we combine those messages to see whether it was a real particle or not. About 3,000 times a second, we record an event, and that happens pretty close to 24/7. So that gets us about 100 billion events in 1 year. Each hole has 60 of those light sensors, and there's 86 of those holes. So a little over 5,000 light sensors down on the ice. And it's kind of hard to see on my small screen, but hopefully you have a bigger screen. But the Eiffel Tower is in there for perspective. The instrumented volume height is about 3 times the size of the Eiffel Tower there. Okay, next one. And this shows an animation of an event. The neutrino itself is shown in the red coming in. It's absolutely invisible until it interacts. When it interacts, a charged particle is created. In this case, it's a particle called a muon, which is kind of like a heavy electron. And it can travel kilometers through the ice. As it does that, it creates a cone of light. And basically, those light sensors are just in there recording that. So this is an animation. The way the event display works is, even though there's so many light sensors, you don't see the individual ones there. There's a dot that represents each light sensor in the ice. If one of the light sensors sees some light, it gets colored in. The color just tells us the time sequence. So right now, you have a static image. The colors that are toward the beginning of the rainbow, reds, yellows are the first light, and then the blues are the last light. So now I can look at that picture and say, yep, that was an event that started on this screen in the upper left and went to the lower right. And then the amount of light tells us how much energy the particle had. So higher energy particles produce more light in the detector. Okay? And I'm going to go fast through this. You'll have an opportunity to ask questions at the end. Okay? So I'm going to turn it over to Ian and Dag, and they can tell you about travel and living at the pole.
So to get to the South Pole, you first have to travel a very long way. The first step is usually to go to Christchurch in New Zealand, which is somehow the hub in the real world for communication between the South Pole and the real world. The first one goes to Christchurch, and after that, one does not go directly to the South Pole. One instead goes first to McMurdo at the coast, which whether it's another hub for transportation further to the South Pole Station, which is at exactly 90 degrees south. So the reason for this is that it's a very long way to fly from Christchurch all the way to the South Pole. So one usually uses a big plane, which can land in McMurdo, and then one uses a smaller plane to fly to the South Pole. And this plane needs to have skis, since you cannot land with wheels at the South Pole. So all in all, you might expect to spend something like at least 4 days from you leave home till you arrive at the South Pole. So it's a quite long travel.
So on the next slide, we're down in Christchurch at this building. I'm sorry. We're in Christchurch at a building that's called the Clothing Distribution Center, or CDC. So on our way south, we have to pick up all these very warm clothes that we have to use anytime we go outside down here. There's a whole array of different clothing on there, and I'm sure in some of the later pictures we'll see people wearing them.
So here we see the set which one person has got. You see the big red jacket which one has on the outside. You have the big white shoes on the right. You have many layers of underwear and clothes and lots of things that you need.
So on the next slide, we're flying down on an airplane. So that's, I think, it's a C-17. So that's one of our big jets. This is the picture, this is the same jet that was in the background of the picture Jim used to introduce himself. They're enormous military cargo planes, basically. So you can see there they're transporting some people up and down either side and some cargo in the middle.
So in the previous picture, we saw the plane loaded with cargo primarily, but sometimes when there are lots of people flying down, then one doesn't bring so much cargo, but instead one fills the plane with heat so that you can take more passengers. It's exactly the same airplane as on the previous picture, just with passengers instead of cargo.
Next slide is a view you might see out that airplane. So those are the Transantarctic Mountains. They're super big mountains, but often you can only see the tops that are poking out because there's also very thick glaciers that are flowing through them. Some really amazing views, and unfortunately, we don't really get to see too much of that once we land down here. So it's been a long time since we've seen these sort of views.
So this picture is probably when the big airplane which goes from Christchurch has landed at McMurdo on the ice at the sea, which gets very thick in the winter, so that it's possible to land even big airplanes on it.
Yeah, so I'll just jump in and point out in the background of that picture, you can see what the plane that you'll get on to head to South Pole from McMurdo Station. We'll have a better picture of those in a minute too.
So this is at the McMurdo station. The building you can see is the first building you enter when you arrive in McMurdo, and you will get some kind of briefing of what to do and how things are organized in McMurdo before you get to your room and do other things. And probably the next day or something you would continue to the South Pole.
So these next two pictures are animals that you might see around the coast of Antarctica. We're looking at some Adelie penguins there. There are a couple different kinds of penguins that you'll see at McMurdo Station. And then we've got orcas in the next slide. For us as winter rovers, when we're going down to South Pole Station, we basically don't get to see any of these because we transit through McMurdo Station pretty early in the summer. So at that point, the station is still locked in ice, and there's basically no water to let you see these cute little animals. And then when we leave, it's about the same time of year, a year later. So we've advanced forward to slide 21. It looks like the one with the C-130.
So at the upper picture, you can see the C-130, which is also called the Hercules. A few of these planes, which are equipped with skis, I actually think you cannot buy them with skis anymore, so you have to keep the old ones, which have skis running pretty much forever. And on the lower picture, it's also from the South Pole, where you see people departing and entering the airplane. On another thing, if you look at the left side of the upper picture, you see a round a football-like thing. This is our satellite communication dome. So our phone call now goes through this dome you can see on the left in the picture.
So in the the next slide here, that's the person entering into the main station here. The station has quite a few different names. I think officially it's called the New Elevated Station because it's the third iteration of stations we've had here at South Pole. It's basically an enormous building that's all built on stilts. The idea is that there's a prevailing wind here that very uniformly blows from one particular direction. So the station is shaped like an airfoil such that the wind keeps it from drifting over as much as it would if it were a regular building just built on the surface.
So on the next slide, you can see people walking out to IceCube Lab, which is the building you can see in the remote in front of 3 people. And on the lower picture, you can see people walking back to the station again, probably from IceCube Lab. This day it's a bit more windy, so you can see how the snow moves around.
The next slide is perspective on IceCube Lab. So pretty good-sized building. I'd say the most distinctive feature of it are the towers on either side. Those are basically where the cables from the detector that we talked about earlier all get brought up from under the ice and sent inside to the computers that talk to the DOMs and the power that powers the DOMs. So that building, the way it's set up, essentially the lower floor is sort of a work area and storage, and the top floor is where all the computers live. So anytime we have a computer that breaks, we have to basically walk from the main station out to IceCube Lab. Usually takes somewhere around 20 or 30 minutes to fix whatever's broken in there.
So on the next picture, you can see somebody measuring the snow depth. Above each of the IceCube string, there is a detector called the IceCube to distinguish neutrino events from cosmic radiation. And for this, it's very important to know how much snow is on top of each of these detectors. So there are these metal poles on top of each of them, which we measure several times a year to determine how much snow there is.
The next slide has an awful lot of red cables in it. That's inside IceCube Lab. Basically, what these cables are doing is they take the signals that come from the DOMs and combine them. So each of those cables represents 4 DOMs.
Yeah.
So yeah, there's one of these red cables for each of the 4 DOMs, and they're crossing over to the left-hand side where there's one of our rows of computers. So we have one computer essentially for each string, plus some extra ones for administrative stuff. But we end up with a total of basically 150 computers in IceCube Lab that are involved in data taking.
I'm going to jump in.
Yep.
Sorry, just a couple questions that are coming through. So if you could let everyone know how many people are there with you now, and when you expect the first plane to come.
Okay. Yeah, there are 41 people total here. Of those, I guess, about 3/4 of them are sort of logistics and support people, and 10 are what we call grantees, so they're scientists. Doug and I are the only 2 who directly work for IceCube, and there are several other large experiments down here. We do a fair bit with cosmic microwave background and that sort of thing, and also with climate monitoring. And so there's some scientists and there's some contractors that sort of support that. As far as the first plane goes, real soon. The first plane we'll see at all hopefully will be here in a week, and it's sort of complicated logistics to explain all this, but basically we see some very small planes that come through. They're not changing our net population at all. They're just trying to get through to other stations in Antarctica for the first couple of weeks. And then I think station is forecast to open on November 1st, if I'm not sure. I'm not totally sure about that, but it's basically that day is the day where we're expecting to see the big C-130s coming in. So those are the biggest planes that come here. Those are the ones that almost all people that come to the South Pole to work will fly on one of the C-130s.
Okay, and what's the most important thing that you're looking forward to coming in on those planes?
Fresh food sounds pretty good to me. I know it sounds a little bit weird, but some people are looking forward to the diseases that come through. We're in a very isolated environment here, so we don't get any new colds or anything like that for an entire 9 months when there's no one going in or out. And so these first few planes, it's sort of like some people hide from them and some people go and hang out with the pilots just to be exposed to all this new stuff so that they don't get completely taken out of commission once the C-130s start flying. Anything you can think of? Or? All right. Cool. Any more questions, or should we keep going?
Let's keep going. I can chime in as more questions come in, but I want to make sure we get through some more pictures and then get to more questions.
Sounds good.
So on the next slide, we see what is probably the midwinter celebration. So it's hard to tell, but at least we have a few big celebrations here during the season. In addition to the normal things like Thanksgiving and Christmas and New Year's and things like that, we also have celebration at sunrise and sunset, and also the midwinter.
So the next slide, so since it's such a small community down here, everyone has to pitch in with a lot of things that aren't really your normal job. So one of those jobs is working in the kitchen. So in that little inlay where a couple of us are cooking food. So I'm the guy in the front that's leaning sort of back, and the guy behind me is our maintenance manager, for instance. So we're just in there cooking dinner to give the real cooks a day off. In the inlay are Blaze and Felipe, so they're our predecessors from last year, and they're doing what we call dish fit. They're cleaning up dishes after a meal.
So on the next picture, it's what I think is the race around the world. So once a year we have some kind of very informal race, which somehow goes around the geographical pole marker, so that it actually goes around all of the world. You can either run or you can ski, or there are even some different vehicles or snowmobiles. So, it's all kind of crazy things, and people often dress up in funny costumes. So, yeah.
So the next slide has a few different pictures. So I guess one of the interesting things about this is that there actually are two pole markers down here. The one in the top left-hand corner is what's called the geographic South Pole, which is the one Doug mentioned the race goes around. That pretty well approximates the axis that the Earth actually spins around on. And it's actually a couple hundred meters away from what we call the ceremonial South Pole, which is the one on the right-hand side. Basically, the reason for that is that the ice shelf that the station here sits on, and all the buildings and all that sort of thing, moves about 10 meters per year. And as a consequence of that, the geographic South Pole essentially moves relative to the things on the surface. And that ends up putting it in places that aren't quite so photogenic. So we've got the ceremonial South Pole, so that everyone goes and takes pictures by, and it's kind of in a nice place relative to the other buildings on station. That picture on the bottom left-hand corner is at New Year's. We have a tradition down here where the Winter Over crew draws up designs for the next year's geographic South Pole marker, and we vote on it, and then the pole marker is actually manufactured by the winter machinist. So as part of that tradition, the new pole markers only get released every January 1st. So we've made up a new pole marker, but the design is a secret, and no pictures are allowed out of the station about it. And basically, next January 1st, the pole marker that you see in the top left-hand corner is going to be replaced with the one that we've designed and voted on, and a friend of ours has put together.
So one of the more exotic sports you can do at the South Pole is golfing, and here you can see somebody carrying it just in front of the pole marker.
Next slide is another fun one. I'm not actually sure who that is in that photo, but some people like bringing these really big kites down here that are so big that they can actually pull you around. So some folks are into going kite skiing. I think someone's tried snowboarding, that sort of thing. Like I was mentioning earlier, there's a pretty constant wind out of the same direction down here, which makes it possible to do some of these sort of things outside.
So on this picture, we see what I think are some tourists arriving at the ceremonial South Pole. So what often, I mean, there are some commercial companies that will fly you to the South Pole, and sometimes they can even drop you off somewhere close to the South Pole, and then you walk the last degree or something until you get to the South Pole, so that you can say that you have been skiing to the South Pole.
On the next slide, we have one of the summertime celebrations. I think that was New Year's, if I remember correctly. But you know, down here, people don't really have a lot of things they can do outside of work and eating meals and going to sleep. So a lot of people get into hobbies that you can do indoors, such as learning a musical instrument or learning to sing or perform or whatever. And so this is a band that's just comprised of folks that were working down here over the summer.
So we need to wrap up in like less than 10 minutes. So we're going to go through these slides pretty quick and get to questions, if that's all right with you guys.
Sure.
Okay. So I'll just speed through. And we'll also post the slides for everyone. I'll send out a link so that you can have a closer look. So right now you're seeing the sun go around in one day during the summer at the South Pole. So if you were laying on your back looking up at the sky, you would just see the sun go around and around. And we're getting to some winter pictures now, and a perfectly timed question says, who joined the 300 Club this year?
Oh, I suppose officially the 300 Club doesn't really exist. But both of us did, and I don't know, probably what, a third of the station, something like that? Something like that.
And can you briefly say if what the 300 Club is, for those who don't know?
Sure. The gist of it is that it gets really, really cold down here. And about the coldest it gets in the middle of winter is 100 degrees below zero Fahrenheit. So we also have a little sauna. And it's possible to, partially because we're up so high in elevation here, it's possible to turn the sauna up to 200 degrees Fahrenheit and actually survive in there for a little bit. So we turn the sauna up to 200 degrees Fahrenheit and then run outside on the first day that it's full at negative 100 degrees out. Your body experiences a 300-degree temperature. So you run outside the station and around the South Pole marker and back inside.
Okay, thank you. So we're just getting to the last slide. The picture that's up now is the South Pole Station in the winter. So you see a little bit of stars in the sky, but mostly it's just kind of peaceful and quiet. Let's start with questions unless there's anything else you guys want to make sure to add.
Nope, question sounds good.
Okay, I'm just going to go in order on the call-in list here. So I'll unmute the group from Nils in Serbia. Do you have a question for the group? Okay, so it looks like their question is, where do you get electricity from?
So all our electricity is generated from diesel generator, and most of the fuel is flown in by airplanes. So we have about 100 sites with the LC-130s every year, and each of them will bring some excess fuel, which is offloaded and stored inside of tanks. So it's actually quite expensive to generate electricity here because all the fuel has to be flown 2 hours before it's offloaded.
Okay, next question. Go ahead. In Israel.
Hello. I want to ask if did putting the detectors inside the ice expose it to some radiation, or did it hide the depth to solve the problem?
I mean, it depends what it means. It to some extent will shield it from radiation, but not for all of it. For example, muons can penetrate very deep, which we will see, and it can be confused with the muons which are produced from the muons from the neutrino colliding ice. So that's why we have the IceCube tank to detect cosmic muons and find out which muons are actually created inside the ice.
Yeah. The ice itself is very pristine, so there's essentially no natural radioactivity. That's important because radioactive decays can also produce flashes of light. So there is another detector in the northern, a couple other detectors in the northern hemisphere that are, one of which is in the ocean, and so the radioactive decays from the potassium in the ocean causes additional signals that aren't from outer space or from neutrinos. So.
Yes, yeah. So the neutrinos we are both interested in have a very high energy and can be somehow easily distinguished from the total radioactive decay. But for the more lower energy, it's hard to distinguish.
Okay, we're going to try and check in with the school in Romania and see if they have a question.
Hello, my name is Stefan. I am from Bucharest, and I would like to ask what are the areas of neutrino research today?
So
I'm sorry, we couldn't quite understand that down here full.
Yeah. So the question was, what type of research is going on with neutrinos? So I can answer that one, or if you would like.
No, go ahead.
Okay, so we basically have two main types of experiments that we do. One type is basically using the neutrinos to learn about other phenomena. So just like we record light from stars to learn about the stars, we record neutrinos to learn about big explosions out in space. And so that's mostly very high energy neutrinos. Maybe more than 1 million times higher energy than produced in radioactive decays or in fusion reactions in the stars. The other thing we do is look at the neutrinos themselves, because the neutrinos have very interesting properties that are still being studied. So, for example, as the neutrinos travel, they change from one type to another. There's 3 types of neutrinos, so that's called an oscillation. And so we know what type of neutrino is created when cosmic rays hit the Earth's atmosphere, and then we see how many of that type of neutrino show up in our detector. And so by that way, we're able to tell that they've changed, because at certain energies, there'll be less of the muon neutrinos, for example. So that's, as you can imagine, it's lots of science going on, but that's the 2 broad categories. Either we're learning about the things that have produced the neutrinos, or we're studying the properties of the neutrinos themselves.
Okay, so we have lots of questions coming in, but I think we only have time for one more. So we'll see if the group at the Sophia Vocational High School has a question.
Okay, we don't have a question yet.
Okay, we'll go to Michaela's group.
One more question, please.
All right, if 2 events happen at the same time, like at a really small time difference, do the domes, the sensors, perceive them as overlap?
Okay. So we do get multiple events happening at the same time in the detector, but most often, because the detector is so big, they happen in different parts of the detector, and that's a very tricky thing to sort out. So the time resolution is, as I say, about a billionth of a second in terms of when the event occurred, and the digitizers that record the signal can actually see smaller time intervals than that. So the short answer is that if 2 events actually happened at the same place in the detector, it's real tricky to sort those out. But we have ways that we try to do that, and one of the neat things is we had a group of high school students actually looking through data for just events like that, not necessarily at the same place, but at the same time, and they found examples sometimes of where there's actually been 3 or 4 events that have happened at the same time.
Okay, let's do one quick question from Stefano's group. Sorry we missed you.
Go ahead. Yeah.
Hello, would like to ask you something. How do you spend your free time?
I think the question was, how do you spend your free time?
Yes.
Yeah.
Outside work.
Outside work.
Yeah.
And there are all kinds of different things you can do. There are different clubs. There is a library. There is a big gym. There is, people have different interests and they get together. I mean, some people play games together. Some people play video games together. Some people just read. Some people, it's all kind of things. I mean, some of us have some small projects going on in the machine shop to make something. I mean, you can go skiing. There are lots of things you can do. Of course, there are certain constraints, but yeah.
I think our satellite might have just gone down, but nice talking with all you guys.
Yeah, nice to talk to you.
Okay, thanks a lot, Ian and Dag. We really appreciate you taking the time to connect with us.
Our pleasure.
No problem. Thanks.
Okay, so I think we need to switch back so that we can make sure to see the ATLAS people. We will compile all the questions that didn't get a specific answer and send out responses later this afternoon. And then, like I said, we'll send a link to our PowerPoint as well. Ian and Dag will help answer more questions if you have them, and then Jim will be available for answering questions later as well. So thanks for connecting with us, and we'll switch back to the video presentation.
I'm going to turn on, I will share a little bit here because I'd like to show them something. Let's see if I can show you. This is, I just want to be really brief. I just wanted to show you this so you had an idea. And we only have a few minutes because there's actually about 50,000 people who come through this visitor center in the year. Hopefully they won't all come in 10 minutes, but they might, and that's a lot. But I just wanted to show you, just so you guys can see a picture here that shows you where we are. ATLAS is the one in blue, and how far the other experiments are apart from us. Okay, so it's far away there. CMS is around the ring. It's a 27-kilometer ring. Now, you heard from the South Pole that they're the largest volume particle detector in the world. That gives us envy at ATLAS because we're always saying that that's us, but we're wrong by quite a bit. The big difference, there was a question that I heard asked about radiation or what was formed under the ice. So there might have been a little misconception. The experiment on the South Pole doesn't have an accelerator other than the universe. So what they're measuring are particles coming from the world, coming from the universe, coming from outside. That's why they can detect if there was a supernova or something like that, a big flux of neutrinos passes through. They don't, that's their accelerator. So anything that they get is natural. So any sort of particles coming through are happening, and it's happening all the time. The LHC is an accelerator which is designed to put all of these collisions together and to create the conditions that were just after the Big Bangs, just so that we can measure the first particles that were produced. So rather than sit around and wait and move our detector around trying to catch cosmic rays, which was what we did 100 years ago, we are actually making the collisions happen in the detector. What's interesting to know is that the LHC, the number of collisions we will get, which are many, many collisions, gazillions of collisions we will have. We've had a quadrillion collisions up to now, impossible to comprehend. Everything that we're going to measure in the next 20 years, Mother Nature has already done about 10,000 times in our upper atmosphere. So we know everything that we're doing here has already happened, but we can measure. We've built these beautiful detectors all around the ring so that we can make precise measurements and capture all of that data. Now you might wonder why, and that's a very important question. Why do we go about doing this? We have some really, really big questions. And ATLAS and CMS and the other experiments are just trying to find the answers to those questions. They are, where do we come from? What are we made out of? And where are we going? Very basic questions mankind has always had. We have always looked inside to see what's inside. We found at some point atoms, and we were sure that we had reached the end, and we were wrong. And then we went inside, and we found that there were protons and neutrons, and there were electrons around that. And we were sure we'd reached the end, and we were wrong. And we still look inside, and we look inside protons and neutrons, we find there are quarks. And it could be that that's it. And we have a beautiful model that explains if that was it, this is what we would see. But we could be wrong. We're probably wrong. Okay? We can explain about 4 or maybe 5% of what the universe is made out of. We're missing 95, 96% of the universe. So while we feel very confident, in the past 50 years we've had a model which has made a lot of beautiful predictions which we found to come true, we're still missing a lot. That model doesn't explain everything that's missing. When we look outside at galaxies, we see them spinning. We see a bunch of matter in there, and that they're spinning at a certain rate. And then if we do the calculations and we say, can all of this hold together? Can it spin at that rate? The answer is no. Based on what we see, the answer is no. There either has to be something completely wrong with our idea of how gravity is working, and yet we've seen that gravity works at many different scales very well, or we're missing something. And we call that something dark matter. It's our ignorance. We don't know what it is. Something called dark matter. That's perhaps our next big thing that we're trying to discover. Both CMS and ATLAS are really trying to find that out. What's dark matter? We're also, and these are a couple of the questions. I mentioned to you before, LHCb is an experiment that is trying to understand where the antimatter went. There was perfect symmetry in the universe. A Big Bang happened 13.8 billion years ago. There was this explosion. All the matter and antimatter disappeared. It ran into each other and exploded. When matter hits antimatter, it explodes and disappears. But some dust remained, and that's us. And we don't know why we're just made out of matter, why there wasn't antimatter. Why didn't we all completely disappear? Big question. There are some things in our theories which might explain that slightly, a little bit, but not enough. So the theory's wrong. It's just short. I have a lot of other big questions. Why does your magnet, the little magnet that you hold hold up a paper clip when it's got the entire world pulling on it to pull it down? The entire Earth, all of the gravity of the Earth pulling on a paper clip, yet a little magnet will hold it? Okay, you ever wonder about that? The force of electromagnetism and the other forces are much, much stronger than gravity. We can't explain the gravity. We have no clue how to fit gravity into our model. That's a very, very big question. And maybe in the next 20 years, as the LHC is operating, we'll get an idea of what that is. So those are the questions. This is why. Let me show you very briefly. I'll show you that there's a big accelerator. It's smashing protons together. Let me give you just a little image of what we have underneath it. Do we build underneath our ground? We have a big area where about 80 meters down, actually in the middle of it, where the LHC comes together and collides protons together. We build our detector. Then the detector looks something like this. Yeah, there it is. That's essentially what the detector looks like. It's big. Those little bumps on the left hand of it are actually people. We have the smallest physicists on the Large Hadron Calorimeter, Large Hadron Collider that exists. They're even smaller than the CMS physicists, right?
Oh, yes, of course.
Absolutely. Okay. Yeah. Our physicists are small compared to our detector. Yet we have brilliant ideas. Both experiments are full of about 3,000 people who are exploring and looking at the data. As I mentioned, we have a quadrillion collisions so far that we've gathered, and we've found a few things. We found the Higgs boson, as you guys all knew and you mentioned, and that helps us to understand how particles, how elementary particles get mass, which is something rather important because we wouldn't be here if we didn't have mass. So that's, I just want to show you that. A detector works by identifying different particles that come out when there is a collision. We get collisions 40 million times a second. I think that Angelos mentioned, if I recall, that it's like a camera. It's like a 3D camera, 100 megapixels, let's call it. So it's a very high resolution camera, but it has to operate at 40 million times a second. That's pretty fast. Try that sometime with your camera and see if you can take 40 million pictures in a second. It's a very hard thing to do. That's what we do. Pictures, the beautiful pictures, you'll see some from CMS. We have some from ATLAS. Let me see if I can pick a good one here. I'm looking kind of at random. This is a picture that gives you an idea that it's a way for us to look to see what's inside quarks, if there's something inside quarks, something that we try to do. And then there's also a picture here of possibly a Higgs boson, or maybe not. You never really know when you get a picture like this, but it could have been a Higgs boson. We're starting to be invaded by visitors. We're very happy to welcome them. So maybe I'll stop, and if anybody has a specific question about ATLAS, then I'll be happy to answer it. Otherwise, I'll have to run away.
Okay, thank you very much, Steve. Does any school have any question? You can raise the hand. We're just going to get one question for Steve. Yeah?
You have to unmute.
All right. So does Haifa has a question?
Yeah.
Does Haifa has a question for Steve? Kobe.
Hello from Haifa. We want to ask, what is your next research in ATLAS? What you want to find there? You're going to research the supersymmetry or dark matter or something else?
So the answer is yes. The answer is yes. We're going to look for everything. That's how ATLAS and CMS are both general purpose detectors. And it's very interesting. The past couple years, something very rare happened in science. We had something we were looking for which we were pretty sure existed, or we knew that something existed in that area where we were looking. So, and I'm talking about the Higgs boson. That search was pretty well focused, although there were many other analyses that were going on at the time. Now we're in a very interesting stage that's coming up. We're going to go to higher energy. Higher energy means that we can produce particles of higher mass. E equals mc squared, right? That works. We do that 40 million times a second. E equals mc squared. We can produce particles of higher mass. That's really cool because the particles of higher mass, you don't see them very much. They decay to other particles, and quickly. Quantum mechanics tells us anything that can happen will happen, and it does happen. So those particles of higher mass disappeared in the very early universe, and we don't just see them easily naturally. So as we go up, we will explore. There are things possibly up there we've never even thought about. I mentioned our model is not complete. Maybe it's completely wrong. Maybe we'll come up with something that will hit us over the head. We're going to a region now of exploration where we just don't exactly know what we're going to see. But we have some great tools. Finding the Higgs boson was really key, not just in that it completed this standard model we had, but it gives us a new tool to look. we will explore how the Higgs boson decays. How many times does it decay this way? How many times does it decay this way? At what rate? And we will measure all of this very precisely. And from these measurements, we should get a hint. At some point, what we measure will disagree with the theory. That has to happen. Experimentalists really want that to happen. And in fact, theorists really want that to happen because they have no idea where to go until there's a deviation from our current theory, which we know is shortcoming. It has shortcomings. So we will explore, we will study the Higgs boson. We will also look for dark matter. And we do this in an interesting thing. You'll notice if you look at this image that I have up here that there's a circle in the lower right-hand part. That circle is the plane where momentum must be equal to 0. Right? That's the protons collide like this. So here, we know conservation of momentum. You guys all know it. You all study physics. It has to add up to 0. But by building a detector completely around it, so it completely surrounds the collision point, we can find out if it doesn't add up to 0. And if we find events where there's missing energy in a certain direction, and it happens more than we would expect from just neutrinos, then we might be getting a hint. We might have an idea of what dark matter is.
Thank you very much,
We will look
Steve.
for that. We will look for events like that. Okay.
I just have one question for Steve, and then we have to switch, guys, to down to the CMS Cavern. So one question from Nis in Serbia, Steve, is that what will you do? What will you do? I don't know if the question is personal. What Steve will do if you discover dark matter?
What will we do if we discover it? Well, what we usually do is, one, we write a paper or several papers, and that goes out to all of our colleagues, including the theorists. Well, it goes to the whole world. Everything we do is public, but the people who will read the papers will be our colleagues, the theorists, and they will try to explain. They will look at how much we see of it and under what conditions, and they will come up with a new model which explains everything we've seen in the past and which adds this into it. That's how science advances. And they will tell us what to look for next. So that's probably the most important thing. If I knew what to do with that, how to build a new dark model airplane or something, dark matter airplane model, I would. But I haven't figured out how to make a Higgs mobile yet. So I don't know. All of this research that we do has big implications for the future. And so it will affect, a new theory comes out of this, it will affect absolutely all research from physics to chemistry to biology to everything in the future. It will have big repercussions. But all we're going to do is measure and report our results and let others work on what to do next.
That's a fantastic answer. Thank you very much. Thank you very much, Steve. We need to switch now to go to the CMS Cavern because we are running slightly late. Thank you very much for your extra time. So let's go down to Mahi and Noemi. Guys, now we are going opposite sides, where Steve is located.
Approximately 9 kilometers away from him. Yeah, we are just on the other end of the well, it's not the radius.
Okay, of the LHC ring. So we are located, Zoltan and I are located in the CMS control room, and the most important thing now that you see is that 100 meters underground,
actually exactly below our feet.
Yeah, you can see the CMS detector. So
right,
go ahead,
Can
Noemi.
you hear us?
Go ahead, Mahi. Yes, perfectly.
Can
go
you
ahead.
hear us?
Yes.
Right.
So what you see really not a poster. There are people there.
Oh yeah.
As of the experiment, it is much smaller than ATLAS, just 16 meters diameter.
That means that our people are bigger. It is just a reflection to Steve. Well, I mean, with respect to the detector, of course.
And this is a proof that this is not a poster. So we are really at the experiment. So we have not so much time. So what we plan, here we have what you see in this is the barrel part, and that is the end cap part. This is also a big barrel, and that guy, what you see here, will move soon in the next days and close the CMS experiment. So what is there? This is our big magnet. This is a 3.8 conducting magnet, and what is inside? There are the colorimeters of the experiment and the tracker of the CMS experiment.
So indeed, sorry Noemi for interrupting. So indeed, we have on one hand the same type of detector what the Atlas has, because this is a so-called 4-pi. This is what Steve just recently described, that we have to put our detector parts around the interaction point. On the other hand, however, this detector looks a little bit different from that of the Atlas. We have only one magnetic field, one component, the so-called solenoidal field, and that's what Noemi is just showing. Yes, exactly, the big superconductive solenoid. And we have a slightly different detector component, but the aim is exactly the same. We are kind of a competitors of each other in the sense that we are looking for the same physics, the same phenomenon. Okay, Noemi.
Okay, so to recapitulate, think of the accelerator as a huge underground donut going for 26 kilometers. At 4 points of the donut, think of 4 bubbles. In every bubble, you have one detector installed. CMS and ATLAS are at the opposite of a diameter of the circle. So now we are at 100 meters underground. The CMS detector is open still because think of it as a huge salami. It can be cut in slices. The slices can be moved in order for us to repair and upgrade it. So Noemi had the chance to show you the different layers of the detector, because you can think of it as a salami, but also as a cylindrical onion. It has several layers. Every layer has a specific role. Okay, so now we will move with Noemi.
Yeah, we are going to move. We go to the other side of this barrel, and we try to go inside the vacuum, inside the magnet. Show you what.
So what you are seeing here is getting close to the heart of the detector, which includes the tracking part and the calorimeter part. The silver tube is actually the cover of the beam pipe. Inside the silver tube, you can see it for the whole length of the detector, you have a thinner and much more precious tube that will contain really the bunch particles as they are produced by the LHC accelerator. And we will have inside this tube, so that we don't bother the accelerated particles, the most vacuum that exists, even more vacuum than in outer space, to allow our particles to travel undisturbed and collide in the center of the detector. So these are, what you are seeing are several systems that help us maintain and run the detector at the appropriate temperatures and conditions. And all the yellow scaffolding you are seeing is going to be removed when the detector will be closed and will appear as a perfect cylinder.
So what you see, what I show you now, this is the end cap part, which will come in soon, and we are going to close it. And what is outside the vector? outside the magnet is all muon detectors. They can detect muon particles.
The recipe is always simple, or it sounds simple. In the very inner part of the high energy physics detectors, you have the trackers for distinguishing the tracks of the charged particles. All around them, you have the calorimeters, which force the particles to die inside their volume, depositing all their energy. And if anything makes it outside, then it's a muon, because muons have the ability to interact very, very weakly with matter, so they can keep on going forever. That's why even here now, Noemi and I are being showered by muons, which are coming from outer space, because they dig through the soil. Maybe if you have any questions now that we're inside. Yeah. Maybe if you have questions for what you are seeing, it's good to put them now, because we are really inside the detector.
That's a very good point, Machi. Thank you very much. I would like to take one question from Athens, because they are about to go. They have some class. So let's go to Athens, please, and ask Machi. Whatever question you might have. Now Machi is inside the detector.
Yeah, exactly.
She's at the very center, guys. Okay.
Well, actually, not right at the center, because
very close,
is very close to the center, and that means that the Higgs bosons or all these exotic things happen just about 2 meters away from there. So they are on a very sacred point of the LHC as well.
So
what is
our universe.
But I want to tell you that this is a very, this is a huge scientific instrument. So the fact that you do not know what the parts are, we are here for that. So you can ask, and no question is stupid, because these are very, very special things.
That's correct.
And the thing that we want to bring to your understanding is that here we don't only have very abstract-minded high-energy physicists. We have a whole group of applied scientists, engineers, computer scientists, mechanical, electrical, high-level technicians, simple workers, crane operators, whatever you want. We are a very close collaboration, and we need help from just about everybody. So go ahead and ask if you don't understand, because it's not obvious. So you have no questions.
One question from Athens. I see no question from Athens.
We have.
Okay.
We have more general questions to ask. Just give us 1 second.
Unfortunately, we don't hear it. Stephanie, can you repeat the question, please?
Yeah, the question is, what are the chances of the universe to decelerate instead of accelerate?
Yeah.
A more general question.
Yeah, this is, I mean, to be honest, this is really a question that might be some of my theorist colleagues might attempt to answer, and not me, but from what I know, at least in the existing models that we have of the universe, people have scientific data to believe that we are still in the expansion part of the universe. I mean, soon come will be the other part, but the soon come, I think, will be billions and billions of years ahead. So the scientific evidence does not contradict the models. But this question, I think, should be really, really referred to a very specialized theorist.
Thank you very much. We have a more practical question coming from Haifa in Israel. So, Machi, the question is that what can influence the operation of the detector? For example, can earthquakes influence? Can the moon influence? Or can a train that actually passes on the surface?
Now listen, the basic thing that influences the experiment is what influences your car and what influences also your apartment heating. There are problems of heating and of cooling. All these devices we are discussing here have to be kept cold. Why? Because they are irradiated, and the radiation effects are retarded. The radiation destroys its physical destruction, mechanical effects. is retarded when the material that's being irradiated is kept cold. So you have cooling plant, yes, the closer we are there, and then since you have cooling and we live in an open atmosphere, you have humidity. Our humidity here is very controlled, so it is limited, like it would be in Israel or in Athens. However, if you cool down, you can make water, and we have to be equipped. Actually, what you see, the orange part around the detector, is a very, very elaborate heating system that delivers heating at the end caps of the tracker, at these two caps at the end of the tracker, so that you avoid water being formed all around it when the temperatures will go around minus 10 to minus 15 degrees, which is the optimal point for eliminating as much as possible the effects of radiation. So you have inside this huge cavern cooling systems, gas systems for making the air circulate, and at the end of the experiment, you have some huge, actually, structures around the beam pipe that act also as stabilizers for micro-earthquakes that happen underground the Jura Mountains. Yes, even here we have earthquakes, not like the ones we are used in the Balkans, but earthquakes that can destabilize the beam. Of course, you have also probably read that the passage of the trains nearby the experimental site and the moon tides have been already recorded by the previous experiments, because we are supposed to be measuring nanometers in distance at billions of times per second. So you bet we can measure and we can see a train passing nearby. However, what we are doing here is really, we are doing lots of engineering for being able to have a stable temperature, stable pressure, stable humidity in order to operate smoothly this huge tool.
Okay, thank you very much for this answer. I see, just to say something, that the school in Athens, Έλληνο-Γερμανική Αγωγή, has to go. So we say bye, guys. Ciao. Ciao.
Bye.
Ciao. So I see students now in Nice, in Svetozar Markovic School. Is that correct? Okay. So I give a question to. Can you hear us? Yes. Go ahead with the question.
Hello. My question is there a chance of anything going wrong with the accelerator or a catastrophe happening because of the research?
Okay, thank you very much. So, Mahi, the question is that is about health and safety, and if
yes.
there's something, what are the chances of something going on with the detector?
Well, we can answer this. So actually, when the LHC is running, when we have protons in the beam pipe, nobody is allowed to go underground. That's our primary safety action. If anybody forces the doors, we have very specialized interlock doors lead to these chambers and the accelerator itself. If anybody forces these doors, they will immediately turn off the accelerator. So that's the first thing. We never ever allow persons and the beam together stay in the same place.
Okay. Maybe the students also wanted to know how this huge camera, comprising of thousands of components, if something going on with one of those subcomponents, you know, how do you make sure that everything works smoothly?
We have a very sophisticated computer system. Actually, the console is just behind us. So, Angelos, probably you can show this. Oh yeah, we have a couple of screens over there. We have a system that continuously looks for the sub-detectors. We have approximately 100 millions of sub-detectors, sensitive parts, and each of them needs low voltage, high voltage cooling, probably gas. And if anyone starves of anything, the system immediately tries to solve the problem. If this problem cannot be solved automatically, it will immediately alert the persons in charge. So we have, this means that we have a 24/7 shifts all around, and we have very, very skilled persons to solve these issues.
Excellent. I'd like to go to Bucharest, to Grigor Moasil School. Do you guys have a question to ask?
Yes, our students had a question. It was written in the group chat.
Oh.
I don't know if you remember
I answered the question, Michaela, but does a student have a new question to ask Mahi or Zoltan here?
We will come further because they didn't said yet about a new question. Actually, they wanted to know.
Yes.
Go ahead.
They wanted to know where the neutrinos masses are coming and what are their values. It was written in the group chat, but I think you didn't saw the question. Actually, who or what generates the neutrino masses and what are their values? If you have some remarks regarding to this question.
Okay.
I have a very, very simple answer. Don't know.
We don't know. That's the answer.
The neutrino masses do not appear in the standard model of particles.
So, I just want to cut Michaela and the students. I don't know if you got the answer of Zoltan, but just pay attention to this. Can you repeat, Zoltan?
Yes. So the answer is very simple. We don't know. In the standard model of particles, we don't assign mass to the neutrinos, and for some reason they get. This is a phenomenon that points out from the framework of the standard model and showing that there is something subtle behind it, and that makes our work so interesting, and that's why we have to continue.
Okay. I'd like to go now to Kobe in Haifa. Kobe, do you have a question?
One more question. Is the CMS do any upgrades while the LHC upgrade also?
Yes.
Oh yes. It's like a car and a road. The road is getting better, wider, much nicer. The car has to be upgraded so that it can profit from the road. Certainly we have been open now, that's why you see these slices for adding extra parts in our detector that will increase our capability of recording, so make our camera better, or add protection to our detector because the beams are going to be much more radioactive and powerful. So we have to protect our material as best as we can, usually by ensuring cooling. So we have been working like underground moles frantically for about a year, and it's always an interplay between the accelerator getting better and stronger and the experiments trying to optimize so that they profit from this accelerator performance. So yes, we have been. That's why we are open. We are open because we had to get ready for the accelerator results.
Thank you very much, Mahi.
Welcome.
So I think it's time to wrap up the session.
Probably, yeah.
Because I see the school in Nice, some movements there. Mahi has to go back to work, really, and you know, the time is sort of limited. Just one final question from Nice, maybe.
Yes.
Marco.
We don't have any questions.
Okay,
thank you.
Okay.
Right. So actually, Noemi is showing you the last slice of our detector, which is going to be closing in the next 2 days, and nobody will be able to see it for at least 2 years. So you are the last lucky ones.
Yeah. Wow, really lucky ones. Thank you very much, Mahi. Thank you very much, Noemi, from the CMS Cavern. I would like to thank all the schools and all the teachers in Nice, okay, Elena Gosheva. I would like to thank very much Michaela Garabet in the National College Grigor Moassir in Bucharest. And of course, I would like to thank a big thank to Kobe in Leo Pike Senior School in Haifa, in Israel.
Best regards from me, from Milena Ivanovic, high school teacher, program 2030, last year.
Of course.
That's good. That's good.
Yeah. And you have regards from Kobe. Kobe was a HST teacher in 2012. So we're very happy to see you.
Yeah.
Okay, guys. Thank you very much.
We want to say, Angelo, we want to say thank you a lot for this interesting and excellent meeting. It was really cool to talk to the South Pole, and really cool to see the CMS open and to talk with the Atlas chapter. It was really nice. So thank you.
Thank you very much, Kobe.
Thank you.
Bye, guys. Ciao. Ciao.